Okay, back again. Our next chapter here is going to be on two-dimensional motion, so 2D motion. This is, of course, again, Physics 1. This is lecture number 4. So, when we do motion in 2 dimensions, it's using things that we already have learned, and we're applying them here now to a second dimension. We're just doing them simultaneously. So, a lot of things that you already know are going to also take effect into this chapter. So things that we had talked about like position, velocity, acceleration, all of those things are from the previous chapter a vector. They have a magnitude and they tell you a direction. Not so much position, but change in position, like a displacement, okay, or a velocity or the acceleration. And all 2D motion means is that we're just going to use the 2 directions that we know of. We can also, once we know how to do 2D, we can also do 3D, or you can go into multiple dimensions if you want it without change. So using 2 directions, best way I guess here would be to visually look at it represented here. Let's say that we have this hockey puck moving across an ice rink. And in 1 dimension, you saw the hockey puck moving along in a straight line trajectory here. And you could see that its displacement, its velocity is changing at a constant rate as it moves across the ice. We're going to assume there's no friction or anything and it just moves across the ice in the x direction. If that hockey puck also moves upward while moving horizontally, you would see a 2-dimensional motion, right? So it moves in the x direction, but it also moves in the y direction. So that's the one down below. The B category here is that you see that it does have that same horizontal motion, but it also has this vertical motion so that each time that it moves a little bit in each direction as it goes along. So how can we make this work for us? Well, we have the kinematic equations, which we've used for 1 dimension. We can use the same kinematic equations for 2 dimensions. We just need to break them down so that we have 1-dimension components for each of the kinematic equations. Okay, so what I mean is the first kinematic equation for VF for our final velocity is equal to our initial velocity plus an acceleration times time. These are all vectors. Velocities are vectors. Acceleration is a vector. The time component, of course, is not. You don't have seconds going in any type, but it's here it acts as a scalar on acceleration, so it's actually okay. So if we're moving with velocities that are in 2 directions, we need to add both of those components up. So you can see that the equation above it says, what is the final velocity? Well, I have a velocity in the x direction initially, plus I have an acceleration in the x direction initially, and that'll be multiplied by time. And then I'm going to use vector format. I'm going to say that this is the x direction by saying I hat. Then I also need to add in the y components of it. So again, I have velocity in the y direction initial, plus an acceleration in the y direction. And that's multiplied by time. And then I signify that that is in the y direction by putting the j hat on top. Okay. Now, I just simply add up what is the total final velocity? Well, it's this component plus this component. It has 2 components. We need to add them together. I can't add i's and j's. Those need to stay apart. They need to stay in the x direction or the y direction, but I can add like components. Okay? So I can say that, well, my total initial velocity would be this x component in its I direction plus its y component in the j direction. And then I end up with something over here like Vxi I hat plus Vyi j hat. So I've got both of the initial velocities here, and they're still separated out by their appropriate direction. Both the accelerations are multiplied by time, so I can do the exact same thing by multiplying the ax I hat plus ay j hat multiplied by time. Okay. And you can see here, if we simplify this down, if I have these 2 components, the Vxi plus the Vyi, both in the I direction and in the j direction respectively. These then would be the total initial velocities. The total initial velocities would come down and be the total vector velocity I, the initial velocity. And same with the accelerations. We have some components. We have an I and a j. That would be the vector component A, the total acceleration A with its two components, x and y hat. This works also for all of the other kinematic equations. The other ones, they also work in multiple dimensions. This is kind of just the mathematical way of looking at it to kind of decipher and prove that is possible. As long as we keep the directions separated while we work the equations, we don't have any issues. Okay, so maybe let's move on with a little more in depth here. Some of the problems that we're going to kind of come into are going to make some assumptions on 2D. So they can get a little bit tricky, so I just wanted to make sure we understand what the questions are asking. And I'll give you a couple of examples here. 2D problems can get very tricky. Sometimes when we say it moves x and y, we're referring to horizontal positions. Like if you looked at your desk or your table, wherever you're at, we might call the direction away from you y, and we might call the horizontal direction in front of you x, both of which are taking place on the tabletop. So it's both in a horizontal position. X and y would both refer to something that's in a horizontal position. Other times it may refer to horizontal and vertical, as in the tabletop represents the horizontal axis, and vertically above the table would be the y-axis vertically. So you have to read the problem carefully to understand what's going on in it, and usually it'll give you a pretty good indication. There's nothing in here that we can't visualize happening, and the problem should state what's going on in the problem, and we would be able to decipher which one it is talking about. For instance, if you take a projectile here like a ball and you give it a kick and it flies up into the air, okay, well now we're talking about horizontal being the horizontal plane and vertical being an upward plane. The ball's going to travel upward in. Whereas if you're reading a map, they might say that you want to travel to the left so many blocks or so many miles and then travel up so many miles. They don't mean up in the air, they mean north. They mean travel up, or up is in the direction of the map, however that works. Okay, so hopefully that those two terms, two ways of saying the positions, hopefully that makes more sense now. One can be in horizontal and vertical, the other just dictates to a horizontal type of a map reading. Another one you can look for is projectile motion. Anytime anything states that it is in projectile motion, it will always refer to the horizontal and vertical type of a problem. For instance, like the ball being kicked here. Okay, a projectile motion means that gravity is going to play a part on that. Something is given an initial velocity, it's launched, and it will go through this arc motion that you would probably imagine or think that it normally would follow. Intuition, that's what happens here. So projectile motion would be something is given initial, usually at some type of an angle. Okay, so there'll be some angle involved, you'll have some initial velocity. If there's an angle involved in initial velocity, it means it'll have two components. It'll have its x component and its y component, and it will travel through this arc. So we can look at it at numerous places along this arc and kind of decipher some things out. Here you'll see that Vx, it is given a certain length, it has a certain value, and Vy has a certain value. You'll see Vy is actually a little bit bigger than Vx in the initial here. This is just the way this problem was stated. And as the ball travels up, you see that Vy in the y direction is actually coming down. It's getting smaller than Vx. Vx remains the same. The angle is also getting smaller. So what is going on? Well, in the y direction, we have gravity playing a part. There is an acceleration in the y direction that is pulling down towards the Earth. That in turn lowers the velocity for that direction. There is no gravity in the x direction. So you'll see that the Vx remains constant throughout this entire problem. If we look ahead at all the other ones, Vx remains the same because there is nothing that is slowing it down. There's no acceleration, so there's no change in velocity. So the velocity never changes. It stays the same. As we keep going up, you'll see that there is a certain point where the velocity reaches 0 in the y direction. Okay? At that point, that is known as the peak. It is at its peak of its path. As it comes back down, you'll see now the velocity has changed directions in the y direction. It starts now to come down, and it will come down with some velocity back to the Earth. Something that initially leaves at a specific velocity, and it returns back at the same horizontal measurement, wherever you want to call it here, ground level, right? We kicked it off the ground and it landed on the ground. As long as this is level, you'll see here that the velocity has just completely flipped. Okay, it started off with some initial velocity in the y direction, and it fell with that same velocity in the y direction, but in the opposite way, right? Because gravity flipped it over and pulled it back down. Okay, sorry. Hopefully that makes okay sense as it goes through its arc. I think this is a pretty good demonstration of that, showing that gravity is pulling down and how it affects the velocity in the y direction. Okay, so a couple more things that you'll see in questions. One of them is going to be called, what is the range of this particle or this object or whatever it is? When we say range, we mean what is the distance the object can travel in the horizontal direction. So here they've used it as a capital R. Okay, so something is given an initial velocity, a kick or whatnot, and it takes off. It has some initial theta value to it. It's going to go through its arc, and it's going to end. So what is the horizontal range? Well, that would be from the launch point to the end point. That is its range. So if you see that in a question, that is what it's referring to. What is the horizontal range? Also, you might see them written as maximum height. What is the maximum height of this object? Maximum height would be the largest height an object can achieve during its motion. So that is the peak position would be the highest point. Okay, so a good way to solve for these when it's asking you for what is the maximum height is that at the maximum height, you know that the velocity in the y direction is 0. That is when it is changing direction, when gravity has pulled it down. So you can think of kind of maybe like throwing an object up in the air. There is a split-second point where it leaves my hand, it comes up, it stops, it changes direction, and then it starts falling back down. That split-second point where it stops to change direction, that is the highest point. And at that point, the velocity in the y direction is 0. It went from positive to negative, and it has to pass 0 in order to do that. Okay, so those are things you might see. Range, maximum height. Say that you could vary the angle to whatever you wanted for the angle. Well, which angles would give you the maximum height or the maximum range of an object? Sorry, it's been a long day. Well, think about them a little bit. I want you to think about these problems. So which one gives you the maximum height? If you could vary the angle, which one gives you the most height? And you can think about it practically. If you're going to throw a ball or throw something, I don't care, whatever it is, take your shoe off, throw it at your partner or at the wall, and see, what would give you the maximum height. Well, as you continue to increase that theta, the height increases as well. Okay. So if you keep increasing theta all the way until all of your initial velocity is vertical, okay, that will give you your maximum height that you can do. Now, normally you can't vary the angle to whatever you want, but you can think of this problem. It's asking you just these conceptual questions on what angle would give you the maximum height. Well, an angle of 90 degrees. If you throw an object straight up in the air, that's the maximum that you can throw it for a maximum height. Any angle besides that, and it's going to be less because you're devoting some of this vector to the x direction, hence lowering the y direction. For the maximum range, you can kind of go through a couple of different different angles if you want. Hopefully you'll be able to kind of convince yourself that something too low ends up just hitting the ground. Something too high goes up too much before it comes back down and hits the ground. It doesn't give you the range that you want. The maximum range is going to be right in the middle between those two extremities, right? So the maximum range would be the middle between 0 degrees and 90 degrees. So 45 degrees gives you maximum range of an object. And again, these are just conceptual questions just to get you used to the concept. Okay. Another part on understanding the questions here. If you follow the same steps, we can get about 99% of those questions out of the way. One, when you read a word problem like this, if you can picture the problem, you're halfway there. Draw it out if you can. We do a lot of drawings. I'm going to do a lot of drawings on the board for you. If you can draw it out, it means that you understand what it says. Okay, so just draw it out just like it is telling you what's going on in the problem. If there is a cat running across the street at a specific angle, draw the street, draw the cat, draw the angle, and approximate it to about what you think is reasonable for that angle. Okay, the more that you understand it, and the more you can picture it, and the more you can draw it, the easier the problem becomes. Okay, the next step I like to do is to write down all the givens, all the knowns, what was in my problem that was provided for me. Usually I put these in tables, or I'll have them listed along the side. That way then you're not going back and rereading the problem a dozen times to try and catch something that maybe was said. You have a nice list of everything that was known. Sometimes you're going to need to break down vectors. So if vectors are given at angles, you'll want to break them down right away so you can get x components of it, y components of it, or whatever the components are that you need. Okay? Get everything that is given, break it all down so that you have it in front of you. Third would be to determine what to solve for. Okay, so what is the question asking? Usually located at the end, but read through the question and know, what is the question asking for? Does it want acceleration? Does it want position? Does it want time? What are you trying to solve for? What variable? And usually I'll put a question mark in my lists on wherever it's asking for that variable. Then you look on how to get there. What equations do you have? What equations do you know? What are your resources that have that term in it, given in terms of things that you already know? Okay, look for the equations that have the things that you have that will help you solve for the thing that you don't have. Okay? When you're all said and done, you've ran through the math and you've got an answer. Take a look at your answer. Does it make any logical sense? Okay, if your question, for instance, is what's the minimum distance for a runway at an airport to land a plane, traveling at some velocity with some braking acceleration or something, right? So you'd be looking for the length of the runway. You'd be looking for probably delta x. You'd be looking for a distance. And if your answer is a half a meter, does that seem logical? That a half a meter would be the length of a runway? Yeah, probably not. So you might have something else in there. Units can also help you out greatly here. If your answer ends up being 5 meters per second, that's not what you were solving for. You weren't looking for a velocity, you were looking for a distance. So you might want to go back and check your work and see what was going on. It can help out a lot to know those things, to look back at your answer and say, does this actually make any sense at all? Okay? You don't have to follow these. These are just suggestions that I do, and I write them down every time. And it's the way that I'm going to do it. So if you like the way I do it, follow along. It helps you solve 99% of your problems. Okay? Most problems are going to have you solve other variables before you can solve the one that's in question. Right? So you're like, oh, I really need to solve for time on this problem, but I don't have the things I need to solve for time. You might have to solve for something else. Look at the things you do have that you can solve for, and then get those out of the way, and maybe you can then solve for time using other equations. Okay, so sometimes it's not straightforward. Sometimes you have to go around and try and solve something else, being like, well, I don't have this and I don't have that. Let me solve for that first, because I do know how to do that. Okay, so the big part on that one is don't give up on it. Even though there's not a straight path on finding the answer, don't give up. Try every avenue, try to solve for something different so that you can use it to get to the answer that you're looking for. Okay, and the more that you do them, practice is key. The more you do them, they seem tricky at first, but you start to see these paths, you start to see what's going on, and then you're able to go ahead and make that realization that, okay, I got to do this first, but then that'll get me to my final answer. And this is important in physics. It's important in all your other classes. It's important in your daily life activities. You do it all the time subconsciously. You know, you need to eat. You need food. Food costs money. Money means you need to do work. You know, all of these things are variables to solve a problem that take multiple steps. Okay. So what I want to do here is I'm going to end this lecture here for now. I'm going to take a pause. This is going to be part 1. Let's do some problems with what we've already learned just so we can get used to that before we move on to anything else. Okay?
Okay, so our examples here for chapter 4 are going to, of course, rely on the kinematics. Now, I have written them all up there. I've left X as the default, but have we figured from chapter 2 with free fall that all of our X's can also change to Y's. We just have to keep them separate. They can't be an X and a Y. We have to keep them all. If we're going to go with X's, all those other variables need to be the X components of the problem. So we'll start off with something that's somewhat familiar that we kind of already looked at here. We have a stone being thrown from the top of a building again. This time the building is 45 meters tall, and the stone is thrown at an upward angle of 30 degrees with a speed of 20 meters per second. Most of these questions are going to have multi-parts. So for part A here, we're just looking at how long does it take for the stone to hit the ground. Okay, so first off, I want to picture what's going on. So let me go ahead and draw out a building. Let's say we're up top of the building with our stone. There's maybe a little easement there where we can stand so that the stone will be thrown from 45 meters. And we throw the stone at an upward angle of 30 degrees. Okay, so you can kind of picture this, what's going to happen, right? You throw it upwards with 30 degrees. The stone eventually will turn over due to gravity, and then it's going to come down and it's going to hit the ground. Okay, something like that is going to occur. Now, that initial speed of 20 meters per second, I can put that up here if I want. And that's all that it gave. It didn't give a whole lot of other numbers. 45 meter tall, 20 meters per second, 30 degrees. So how long does it take for the stone to hit the ground? Well, on our normal 1D problems, when we were talking about this, we would always make a table. Okay. With this one, we actually have 2 dimensions that we're talking about. It moves in the X and it moves in the Y. So what you want to do here is have 2 tables, right? So we can have the change in X, the change in Y, and then under each one, I'm going to put down the 5 variables that we're familiar with: velocity, initial and final, acceleration, and time. Now what I want to do is figure out, well, what do I know and what am I solving for? Okay, so I'm just going to put this over here. Lots of information that we can look for here. And we'll just go through them and see. Okay, so given everything that's in the problem, I'm going to look for maybe a delta x. That's this distance here, right? It would be the distance, something along the x-axis. Not really given that. I don't know. It doesn't say anything except for the building is 45 meters tall. So the 45 meters tall would be the what? It would be the change in y, right? So if we start at 45 meters tall and we go all the way down to the base, to the ground, the stone will have traveled 45 meters. But it has traveled in a downward direction, right? So its final displacement is 0, and its initial, its final location is 0, and its initial position is 45. So I have 0 minus 45, which would give me 45 meters for the y. Okay, so I don't know this one, but I do know that one. Okay, and now we look at the initial velocities. Do I know the initial velocities of either the x or the y? And it turns out I actually have both, but they're represented by a polar coordinate vector. So I'll have to do a little math. I'll have to break down that vector before I can put those numbers in, because 20 meters per second is neither x nor y. It's a mixture of both. Okay. So what I want to do here is let's draw out a triangle. The hypotenuse of this triangle is 20 for the meters per second. The angle in here is 30 degrees. Okay, same as it was given up in the problem. And I am looking for the x and the y components of that triangle. So back to the previous lesson on vectors, how do we find that x and that y component? Well, we have to use SOHCAHTOA. Being x is adjacent the angle, if it's adjacent, that's the A of SOHCAHTOA, which means it's going to be a cosine. So again, if we remember out, we have cosine of the angle. What's the angle here? 30 degrees. Okay, is equal then to the adjacent, x, over the hypotenuse, 20. So to figure out x, I'm going to have 20 times the cosine of 30 degrees. Okay. So let's grab a calculator. Let's figure out what that is. 20 times the cosine of 30 degrees gives me 17.3. Okay, so the x portion is 17.3. And what's the units? Well, it's the initial velocity. It's the same as the hypotenuse. It's meters per second. Now for the y, we're going to do the same scenario. We look back at SOHCAHTOA. We look at the one that has opposite over hypotenuse. That includes the angle. And we go with sine, that one is going to be sine. So I know then that 20 times the sine of 30 will give me the y. Okay, so let's do that. 20 times the sine of 30 gives me 10. Okay, and this is 10 meters per second. Okay, so that got us some answers for some of this. So that means that this initial 20 meters per second that it told us was at 30 degrees is really 10 meters per second in the y direction. Well, that's the initial velocity in the y direction, 10 meters per second. And how much initial velocity does it have in the y direction? In the x direction? That's 17.3. So I can add that in there now. And you'll find that most of these problems initially, it'll always usually give you something like this where it's in that type of a form. And you need to go ahead and break that down right off the bat. It's usually an initial velocity. It may be, it may state the final velocity at an angle. It might even give you an acceleration at an angle. All of these things, if they're at an angle, we need to get rid of that angle right away and break it down into its component form by using SOHCAHTOA so that we can add it to our tables. It's the only way to get to our tables. Okay, now we have the initial velocity. Let's move to the final velocity. This is where a lot of students make mistakes because they assume the final velocity is 0, that the stone has hit the ground and come to a stop. That's what you would normally see in everyday life. You would imagine that, yes, the stone has hit the ground, but it hit the ground with some velocity, correct? It did move. It was moving just before it hit the ground. The ground is what stopped it. So the final velocity, we don't want to put 0 because the stone was falling when it hit the ground. Okay, it wasn't stopped when it hit the ground. It was falling when it hit the ground. So we cannot put the final velocity at 0. That throws everything off because we're assuming now it has gone through a sudden acceleration to a stop. Okay, so we have to leave the final velocities alone right now because we don't know at what speed did it hit the ground. What else do we know? How about acceleration? Do we know anything about acceleration? Well, this is a free fall object once it leaves our hands, right? The rock doesn't have any type of booster engines or anything like that that's going to give it some type of an acceleration, which means it's a free fall object. Free fall object means that I can put in a negative 9.8 meters per second squared for the acceleration in the y due to gravity. In the x direction, is there anything pushing on it? No, not really. So in the x direction, we have zero acceleration, or 0 meters per second. Well, now if there's zero acceleration, what does acceleration mean? Right? Acceleration means change in velocity. If there is zero change in velocity, zero change in velocity means that the final velocity must be the same as the initial velocity. Okay? And that's coming from the equation A is equal to change in V over change in T. If this is zero, while time passes, that means this has to be zero as well. So the change in velocity final minus initial has to be zero as well. And lastly, what about T? Do we know anything about T? T is what it's asking for. How long does it take for the stone to hit the ground? So T is our variable, our question. But which T? Which one is it? In fact, it doesn't matter. The T is in both the directions will be the same. All right. Any object that travels in the X a certain amount and in the Y a certain amount, it travels in the same amount of time. The time it takes to go from the top of the building down to the ground beneath, even though it traveled in 2 dimensions, the time here will be the same. So it begins with question marks, and they'll both be the same no matter how we solve it, either using the X or using the Y. So how do we want to solve this? Well, I need 3 things, and both sides of this equation have 3 things. So theoretically, I should be able to go ahead and pick anything that I want. So what I'm going to do here is I'll grab an equation. Let's use the x's as our example. Okay, we'll use x. We're looking for t, and the thing we don't care about is change in x. So I look up and I wonder which one does not have the change in x. It's the first equation. First equation does not deal with x, and I get VF is equal to VI plus A times t. Okay, so I want to solve for t, so I start plugging in what I know. I have 17.3 is equal to 17.3, which is equal to 0 times t. 0 times t is going to be 0, and I end up with an equality. 17 is equal to 17, or 17.3 is equal to 17.3. So what did I do wrong? What happened? Where did we go? Well, guarantee you're probably going to make that mistake once or twice before you realize that we got lots of kinematics and lots of ways of finding the solution. If you run into a problem like this, where it cancels out the variable that you're looking for, you just look for another way. Look for a different formula. Look for something else that's going to get you where you need to go. Don't get hung up that we've made a mistake. We technically have, and 17.3 is equal to 17.3, but 0t is going to knock our variable t to nothing. It doesn't mean t is 0. It just means t won't be a factor in this equation. So we made an error. Let's not go with that. Well, what other options do I have? I can move over to the y's. Okay, I also have 3 things in the y. Let me use the y's to find t. Okay, so that one I do have a change in y. The thing I don't have, or I don't care about, is the final velocity. So I need to come up and I need to pick one of the equations that does not have final velocity. And you'll notice that's the 3rd equation. Okay. Now I'm going to substitute in change in x to be change in y. So we'll start off with a negative 45 because that's our change in y. Equal to the VI. I need to use everything off of the y column. So this VI needs to be 10. Okay, it'll be 10. T is the thing we're looking for. Okay, time. Plus 1/2 times A. Our A is a negative 9.8. And then, of course, this will be times t squared. Okay, now what do we do? So I've got t in there twice. One is squared, one is not. So if I added this 45 to the other side, we'd end up with a 0, and we'd have a factor with no t, a factor with 1t, and a factor with a t squared. And that's known as a quadratic. So that would be a polynomial or a quadratic, and we need quadratic equation in order to solve that. Okay, and some of you might know the quadratic equation, find it simple and easy to work with, and of course you can go ahead and solve it. It will give you two answers for time is the problem, and you need to be able to decipher which one is the correct answer. In this case, it would give you one that is a negative time and one that's a positive time. And you, of course, go with positive time, being that positive time has passed while the rock fell down. But there is a trick to get around this quadratic, okay? And that is you're looking for time and you're avoiding VF. So do it in the opposite order if you don't want to use the quadratic formula. So I'm going to go with it that route, okay? I'm going to take that route. And I'm going to say, well, I don't like the way that this equation is working either. I'm going to pick another equation and try that. So the only thing left is the VF over in the y side. So I'm going to solve for VF first because it prevents that quadratic from popping up. So what I want to do for the VF would then be that t is the variable I do not care about. In that case, then I would use the fourth equation. Okay? The fourth equation being VF squared is equal to VI squared plus 2a change in y. Okay, so VF squared is what I'm looking for. I guess I don't need to put in parentheses if it's the variable I'm looking for. And again, we're doing all this to eventually get to time. I'm running into roadblock after roadblock. I'm just doing this as the example of when you hit a roadblock, keep going, keep making the progression, keep following it through. VI we know. VI is 10. So I'm going to go 10 squared, so it's VI squared. Plus 2 times A is negative 9.8, times the change in Y. And the change in Y for this one is a negative 45. Okay. So now we grab our calculators. It's nice because everything is on that side of the equal sign already. So 10 squared is, of course, 100. And we're going to do the rest of it. 2 times this negative 9.8 times this negative 45. Okay. And what we get for our answer for VS squared is going to be 982. But this is squared. So we have to take a square root on both sides to get us our final velocity, to get a VF. So if we take the square root of our answer there, 982. Yeah, 982. I don't know if I mispronounced that earlier, but 982. We get 31.3. Okay. Does our answer make sense? 31.3. We only threw the rock with 20 meters per second, but it went up and then it turned around and it came crashing back down. It had a pretty long distance to fall, a 45-meter long distance to fall, so I think it would have gained some speed on the way down. So I think 31.3 meters per second probably makes some sense. Okay, it's probably a logical answer. Now, if I want to add that to my table so I can use it to find time, I also have to be careful that I took the square root of a square. If you're doing that, the initial, the VF, the variable in question, could have been positive or negative because you were squaring it, it didn't matter. So it could have been something that was positive or negative. For the velocity, which way is it traveling, right? The final velocity, initial velocity is positive, traveling upward in the y. Final velocity is falling, right? So the final velocity here should be a negative 31.3 meters per second. Yeah, 31.3 meters per second. All right, now that we have final velocity, we can finally solve for time without using the quadratic. And how do we do that? Well, we need another equation. Now, I need one that solves for time and doesn't give me that quadratic. So initially we had chosen the third equation because that had given me the quadratic function. But now that I have all four, I can actually pick from any of these, 1, 2, or 3, because I have the final velocity. So I'm going to default to number 1. It gives me the time, it doesn't care about the position, and it has my two velocities that I now have. So if I'm going off of 1, I'd want the final velocity, which we just calculated, to be negative 31.3, equal to the initial velocity for the y direction was 10, plus its acceleration, the negative 9.8, and that now solves for t being our only variable. Now t's all on its own, so I can go ahead and solve this one out. First thing I'm going to do is, of course, minus that 10 to the other side, and then we'll divide by 9.8. So I'm going to minus 10, that'll give this a 41.3, and then I'm going to divide by that negative 9.8, and it should just leave a t over here. And hopefully that makes sense. Minus the 10, divide, and that should leave a t. Now, if we look at 41.3, negative 41.3, divided by a negative 9.8, the negative signs will cancel, and we'll come up with a time of 4.2. And that, of course, is in seconds because everything else is in SI units. So that'll default down to seconds, 4.2 seconds. All right, does that seem realistic? 4.2 seconds for a stone to fall from a tall building. Yeah, that's probably okay. If it was anywhere longer than that, like a minute or something like that, we'd probably have some error. But 4.2, that sounds reasonable, 4.2 seconds. So we'll go ahead and add that to our table. And the beauty of this is it can go in both places. Takes care of both of the times because they both traveled at 4.2. Okay, so a second part of this or a third part of this would have been, finding final velocity in the y direction. The only thing left to solve is the change in x. How far did this thing go from the building to over here, from the edge of the building to there? And we can solve that if we want. We can make that part B if we needed. We have 4 out of the 5 things for x, so I might as well finish this one out. You'll notice in most of my assignments or in my homeworks or your questions on there, they're going to be multi-part, so you're most likely going to be solving for all of it anyway. So if I want change in x and I have everything else, I'm free to pick any of the equations that have the change in x in it. So 2, 3, or 4. Okay. Let's see, we've already used 4. We tried 3 and it didn't work. Let's work with 2 so we just get a variety here of problems. So I'm going to look for the change in x. I'm going to use equation 2, and that's going to be equal to 1/2 of the initial velocity, 17.3, plus the final velocity, 17.3. Notice I'm looking at x, so I'm grabbing x's from the x column, and I need the t from the x column. It's the same in the y, but it's 4.2 seconds. And let's look at the change in x. So 17.3 plus 17.3 is exactly 2 times 17.3. If we took a half of that, we end up back at 17.3. So it ends up just being the velocity times the time of 4.2. And we get an answer here of 72.7. Okay. And we look at it and go, does that seem right? 72.7 meters. Well, the building's about 45 meters high, so I don't think my drawing is super accurate there. But it is in the ballpark region, right? It would actually be somewhere out in here, I think, is more where the stone would go. So let's look at another example, number 2. So this time we are at a bar. A person slides an empty glass down the bar and off the end. The bar's height is 1.22 meters, and the glass hits the ground 1.4 meters away, so away from the end of the bar. Question asks, what velocity does the glass leave the bar? Okay. So first I got to picture this. I got to come up with a pictorial. So I've already drawn a picture of kind of what's happening. Here's our person of interest, dressed as a cat, looks like a cat. I think it's a cat. Takes that empty glass, pawing at it, knocks it down to the end of the bar. Why is there a cat at the bar? I don't know. Anyhow, glass falls off the end of the bar, as cats do, and it crashes to the ground. Okay. The bar's height is 1.22 meters, so I have the height of the bar as 1.22. The glass hits the ground 1.4 meters away, so I have this distance here as being 1.4 meters. That's where the glass hits the ground. Now, it's a two-dimensional problem. We can see from the picture, we can see from the wording of it that it has a height and a distance, and it's asking a two-dimensional kinematic. So I have gone ahead and made my two tables. Okay, and now we're going to try and fill in those tables as best we can. So what information do we know? Do we have a change in x? Yes. Okay, so the change in x is the distance at which the glass left the counter and hit the floor. So our x displacement is 1.4 meters. Now, I don't always write the units on these. I want your units in the final answer. I don't care too much if you have the units in here. But we'll have 1.4 for our 1.4 meters for our change in x. How about the change in y? Do we know that? Yes. That is the 1.22, okay? But it fell down. So we want to make sure that it's negative. Negative 1.22. All right, how about the initial velocities? Do we know anything about the initial velocities? What was the initial velocity in the x? Well, that I don't know. That's what the question is asking. What is the velocity? What velocity does the glass leave the bar? Okay. So velocity in the x, I don't know. How about velocity, initial velocity in the y? Do I know that? Well, if the bar is horizontal, nothing pushed the glass down. It simply slid off the end of the bar. So what direction was the velocity traveling in? Velocity was 100% in the x direction only. So when the glass or the whatever it is leaves the bar, there is no velocity in the y direction. Okay, so it's these subtle things, being able to read them and draw them and figure out what's going on. It's these little subtle things. So there's no velocity, no initial velocity in the y direction. There's no speed up or down on the glass. The glass simply goes off and then begins to fall. How about the final velocity? Again, some of you want to put zeros for that. We cannot put a zero because yes, it does hit the ground, but it hit the ground with the final velocity. It had to be moving in order to hit the ground, so we don't put a final velocity number in there, or we don't put a final velocity of 0 in there. How about the acceleration? Do we know any of those? Yes. So this is a free fall, right? The cup is falling under its own weight, under its own due gravitational acceleration. There's no jet engines or anything crazy. It's just naturally falling due to gravity. So if that's the case, we have 0 initial acceleration here for the x, and we have a negative 9.8 for the y. I might as well go ahead and put the units in, that's fine. Okay. So hopefully that makes okay sense. By now we have 0 acceleration in the x because there's no gravity in the x direction, but there is gravity in the y direction, and that pulls down negative 9.8. How about the time? Do we have anything to do with the time? No, other than the fact that the two are going to be the same time. I don't know what the time is in the x or the y, other than that they're going to be the same. Okay, so not a whole lot here is given. This is what I want to find out, right? The initial velocity in the x direction will be the total initial velocity at which it left the bar. But I can't do anything in the x because I only have 2 bits of info and I need 3 bits of information in order to solve this problem. So what am I going to do? Well, I really need to get some information from the y and bring it over to the x. And the only piece of information I can do that with is the time. Okay, time is the same in both. So which means I need to solve for the time here. Bring that information over, and then I can then solve in here for the initial velocity. So I need to solve for time, which means the variable I do not care about is VF. Okay, so if I don't care about VF, that's the one that I want to go ahead and put in. So what equation does that tell me to use? I look up for the one without VF, and I see we have the third equation. Okay, let's try the third equation. Last time we tried it in example 1, we ran into issues. Not always the case. Let's see what we can do. So I'm going to deal with the y. So I'm going to have the change in y. That's going to be a negative 1.22. Okay, going off the third equation, we have change in y, negative 1.22, is equal to the initial velocity. But the initial velocity this time is a 0. So 0 times t plus 1/2. Our a is negative 9.8, and this will be t squared. Now, normally this would be quadratic, and we'd need to use the quadratic formula. But because we had 0 initial velocity, it cancels out one of those t's, which is a big help for us. Okay? Cancels out that, makes that very, very nice. So now all we have to do is we have 1/2 of this negative 9.8, and we need to divide that over to the other side. Okay? So what do we get there? We're going to have a negative 4.9 getting divided over. So I'm going to have a negative 1.22 divided by a negative 4.9, which is half of 9.8, is equal to t squared. Okay. Now to get rid of the square, take a square root on both sides. The two negatives will end up canceling anyway, and you'll end up with a t, okay, a time. And what do we get for that? If we do a square root of 1.22, well, negative 1.22 if you want, divided by a negative 4.9, you get a time of 1/2 second. All right, does that make sense? Half a second or 0.5 seconds. Do you think it takes about a half a second for a glass to hit the floor when you drop it off your counter or your cat's being a butt? Yeah, I'd say that's probably right. So that means our time then would be about a half a second. And I can put it in both columns, half a second. All right, now that I've got 3 bits of information over here, now I can look more at the initial velocity part of it. For that, the thing I don't care about is VF, right? If I don't care about VF, which equation would I want to use? Right back to the third equation again. So let's use the third equation. Okay, we've already used the third equation once for y. Now we're using it for x. Okay, and we're solving for something different. So we're using the equations, solving for different things depending on what's given. Third equation doesn't have VF in it. We want VI. Okay, delta x out of my x column is going to be 1.4. The VI is the thing that I'm looking for. T just discovered is 0.5. Okay. Plus, we have another 1/2. What is the acceleration? Big fat 0. And then the time is 0.5 squared. But because we have a 0 in there, this whole thing goes to 0. It just cancels out, right? It goes to nothing. So that means our initial velocity here, we just need to divide by 0.5, which is the same thing as multiplying by 2. And this will give us an initial velocity of 2.8 meters per second. Okay. So if we want, we can go ahead and add that to our table. But the thing we're looking for here now is our initial velocity, 2.8 meters per second. Okay. So here's actually our answer to our question. 2.8 meters per second. Does it make sense? Yeah, we've only done a couple of examples for velocity, but I think you've got a little bit of a knack for them now where 2.8 isn't actually that fast of a thing. So sure, I think that's fine. That looks pretty good. If we were to expand on this, if we were to do other things, we would find the final velocities, okay, for that cup. Okay, and we can do that if we want. That's fine. Sometimes they'll ask you, sometimes they won't. But what will you do to find the final velocity? Now that you have all of that information, what would you do to find final velocities? Well, for x, it's very easy, right? For x, it's very easy. And why is that? Well, you could grab one of the equations and run it through and get a final velocity. But what you realize is a is 0. You have no acceleration in the x. Your final velocity will be the exact same as your initial velocity every time you have no acceleration. So that part's nice and easy. Okay. For the final velocity in the y, well, that one, there is an acceleration. We would need to pick a formula for that. So why don't I just grab the first equation, first formula, because it already is driven towards VF. So I have VF is equal to VI. VI over here is 0. Okay, easy. And then plus my acceleration, which is negative 9.8, and then times my time, 0.5. All right. 0.5 of negative 9.8. What does that give you? Should give you a 4.9, a negative 4.9. So our VF is equal to a negative 4.9 meters per second. Does that make sense? Well, if you got to think the glass is falling and it's falling towards the ground, yeah, we would have a negative 4.9 meters per second for our final velocity. So you might be wondering, well, why is one negative and one's positive? Okay, final velocity here is falling downward, whereas that glass is still traveling in the positive x direction, negative y direction. So one's positive, one's negative. It's all relative to the problem. It depends on what's going on in there. That's why you have one that's positive and one that's negative. Okay, so hopefully that makes sense. You see here that they are not 0. They're not 0. One is traveling this way, and it's traveling down when it strikes the ground. And again, we filled everything out. There's no other questions I could ask you on this one because we have found all of them. All right. Example 3 here is going to be pictorial. To write all this out would just take up a lot of board space, so I'll use a picture here to explain the third example. Here we have an American footballer kicking a football. He kicks the football with an angle of 53 degrees and an initial velocity of 20 meters per second. We know that football is going to travel upward in an arc, and it'll come back over here near the goalpost. Now, where exactly it's going to end, I don't know. Is it going to go through the goal? Is it not? That's actually question A, is will it make the goal? Now, the goalpost is 3.05 meters tall, and the kicker is 36 meters away from the goalpost. So that's our first question, is will there be enough height to make it through the goal, or will it fall short of the goal? Okay. Part B says, is it traveling up or is it traveling down at that point? So is it still on the upward climb as it goes through the goalpost? Or did it just barely make it? It already reached a maximum height and it's now falling as it goes through the goalpost. So that's the travel up, travel down. And part C says, well, what is the highest point that it will reach? So what is the maximum height? How high will the ball actually go? Okay, so that's our 3 questions. And we should now have a good practice on this to go, yes, this is a 2-dimensional kinematic problem, especially because it gave it to us at an angle and we know there's vectors involved. Definitely a 2-dimensional problem. So I've drawn out my tables and I'm going to start filling out everything that I know. So if I look at the x direction, I know now that the change in x He is 36 meters away from the goalpost. I will write this down as 36 meters. Positive direction, because that's the way it's traveling. Should be fine there. What about the change in y? Is that going to be the 3.05? No, right? Because the 3.05 is the reference, right? We need to figure out what the change in y is to determine if it's above 3.05, it makes it through the goal. If it's below 3.05, it has failed to make the goal, to go through the goalpost. So the change in y is what we're looking for in this problem. How about the initial velocities? We got those figured out? Well, same as before. We have a vector here. We need to break that vector down. So it starts off with 20 meters per second. And there's an angle here of 53 degrees, which means I'll have an x component and a y component. Okay, I'm guessing we've done enough of these now where we kind of start to figure this out with our trig, is that this is adjacent, the x is adjacent to the 53, which means we're going to be using cosine. So I need the hypotenuse times the cosine of 53, just like our previous examples. For the y, that is opposite, so I will need the sine of 53 for those values. Okay. Now when I plug those in, what do I get? Well, for the cosine of 63, for the cosine 53 times 20 for the x side of it, I'm going to get around 12 meters per second. And when I do the sine function for 53, I get 16 meters per second. So plug into your calculators, make sure you're actually getting those numbers, make sure you get everything correct and how it's supposed to go. Okay. How about the final velocity? Do I know that? Well, no, this one has nothing to do with the ball hitting the ground. I don't know what the final velocity is as it goes through the goalpost. It's not talked about and it's not asked about. So the final velocity, I do not care. How about the acceleration? Do I know anything about that? Yep, we should be able to recognize now that this is a free fall object, which means we'll have 0 meters per second squared for the x and a negative 9.8 meters per second squared for the y. And how about time? Do I know anything about the time? No, wasn't given. Wasn't asked in the questions either. Okay. Well, in order to solve for what I want, the change in y, I need three things in the y side, and I just don't have it. I have the acceleration, but I don't have time. I don't have final velocity. So I need another bit of information. So we have to go over to the x and get our time so I can bring time over to the y. Okay, so hopefully that makes sense why we need to do that. I need three pieces of information for this to work. I then need to look somewhere else for an answer. Okay, so I'm going to solve for time on the x side, bring it over to the y side so then I can solve for delta y. All right. So let's look. If the thing I want to now solve for is time, and I don't care about VF, that brings us up to our third equation, which can always get a little bit messy depending on if we have quadratics or not. So let's try it. Let's plug in. Let's see what happens. My change in x, if I'm on the x side, is 36. My initial velocity on the x side is 12. All that'll be multiplied by t for time. And then I'm going to have a plus 1/2. My a on the x is 0. All right, and then there'd be a t squared here. But 0 times anything is 0, so that kills this whole side of the equation. I now don't need to worry about it. Now all I have to do is just solve for t. And that's easy enough. That's 36 divided by 12. That means t is equal to 3 seconds. Okay, 3 seconds can be brought over onto both sides. Okay, does 3 seconds make sense to you? 1 1,000, 2 1,000, 3 1,000. For a football kick, I don't know if you've ever been to a football game, but I'm sure you at least have seen it somewhere. That 3 seconds, that's perfectly normal for something like that. A little For the fans that are in the crowd, if this is the winning kick or something, it's probably a little nail biting for 3 seconds. But that's fine. We can use it. Great. Now I have 3 bits of information. I can finally now solve for the change in y on the y side. Now, what equation do I need for that? Well, once again, we don't care about VF. And if we don't care about VF, we use the third equation. This time we're solving for change in y, so I'll leave that for change in y. The VI on that side was 16. The time was 3 seconds. Plus, we're going to have 1/2. Our A is going to be a negative 9.8. Okay. Gravity coming down. And then T would be 3 squared. All right, so no need to manipulate the equation. We can solve right out for the change in y. And what do we end up getting? Hopefully, you get 3.9 meters. So what does the 3.9 meters tell us? Okay, well, the 3.9 meters tells us that we are above the 3.05 and that this ball goes through the goalpost. So will it make the goal? That was a lot of work for a yes or no question. Okay, lots of work for a yes or no question. But you have to show me your work. If you don't show me your work on how you got there, there's no credit for that. I can't just state yes or no. You have to prove it. Why? Okay. How about part B? Is the traveling up or down at that point? Well, up or down relates to the y, right? And traveling refers to its motion, its speed, right? Is it traveling with an upward velocity or a downward velocity? Which means we now need to solve for VF at that location. So this is now what it's looking for part B. What is the VF? Is it positive or is it negative? Is all that it's asking. Positive or negative at that location? Well, we don't know. Without looking at it, without doing the math, we don't know. So we have to go ahead and do that. Okay, so take this out of here. Now we need to solve for VF. I have every other piece of information. I can pick any of the equations that I want as long as it has a VF, so anything but number 3. Let me grab number 1 because number 1 is my favorite and it solves for VF right away. I don't need to move anything around. The initial velocity was 16 plus our acceleration, negative 9.8, and the time was 3 seconds. Okay, so all you have to do now is just plug that into a calculator. 16 plus a negative 9.8 times 3 gives us negative 13.4. VF gives us a negative 13.4. So was the ball traveling up or down? It's negative. So it's traveling in the downward direction, which means my picture over here changes to something that went up and then barely made it through the goalpost. Okay, barely made it through there because it was just a little bit above it and it was already on the downward trajectory. Okay, so now it paints a little different picture. How about part C? What is the highest point it will reach? Okay, so what's the highest point that ball will reach? Well, these tables, I don't have anything else except for final velocity here, but actually I already know what the final velocity is because I have 0 acceleration. So all my tables are full. And it's asking what's the highest point it'll reach. There's more parts to this problem. So what do you do now? Okay, you start back over again. What's the highest point the ball will reach? Let's give it some new numbers. Okay, let's think about it. Let's give it some new numbers. At its highest point, where is that? That's here, right? That's its highest point. Okay. What's the delta x? on that at its highest point? Well, I have no idea, right? It didn't tell me any of that. I don't know. How about its initial velocity in the x direction at its highest point? Okay. So that does tell us something. Okay. The initial velocity I had before. What was the initial velocity? Well, it was 20 times the cosine of 53. Okay. Which was 12. It is still traveling at 12 meters per second at that point because it travels at 12 meters per second throughout the entire thing, which means this is also 12 meters per second and this is still 0. Okay, hopefully that makes okay sense. All right. But these now remain unchanged. I still don't know anything about the time it takes to get up there. I don't know. What else do I know? Okay, how about the change in y? Change in y is what I'm looking for now. What is the maximum height, right? What is this height? That's now what I'm looking for is the change in y at its highest point. Okay, how about initial velocity in the y? Do I have that? Yes. Okay, it was still kicked with 20 meters per second, so this will remain unchanged. It is still 16 meters per second. But now what's the final? I'm not looking over here anymore. I'm now looking up here. And if we remember, the final velocity in the y direction at its highest point is when an object comes up, briefly stops, and then changes direction. So this problem has changed to 0 meters per second for the final velocity. Acceleration, that remains unchanged. We're back at negative 9.8 meters per second. And time, again, I don't know, don't care. Okay, now at least I filled everything out that I can with this new question that was asked. And I need to figure out what the change in y is for this new question. Okay? So I have my 3 things. I can now figure out the change in y. The thing I don't care about is t, which means equation 4 will be the one that I want to use for this. Okay, so equation 4 says, I'll write it out, vf squared. We don't use equation 4 too much, so I'll write it out here for us. Vf squared is equal to vi squared plus 2a change in y. We just grab off of our table. This is a 0 squared. This is a 16 squared plus 2 times a negative 9.8. And that's how we'll solve for delta y. Okay, so 16 squared, what does that give us? It's going to give us a negative 256 over here when I minus it to the other side. We have 2 times 9.8, that gives us a negative 19.6 change in y. And now I just need to divide both sides by the negative 19.6. And that will give me a change in y of 13.1. Okay, so I can add it to my table. It's also the highest point that this will reach is 13.1 meters. Okay, so he overshot it quite a bit. Could have brought that angle down a bit and made it a little bit more secured goal. Ball went all the way up to 13 and then fell down, barely made it in the goal post. Okay, so hopefully this makes okay sense. It's a one question, one pictorial. It asks 3 questions. We end up having to do that a couple of times. There's one in your homework where you'll have to do the whole thing twice. I just want to make sure we get that covered, so that sometimes when you fill everything out and your question looks like a brand new problem asking new parameters, start over. Get them all new parameters put in. See what you can use from the previous work, previous stuff. Transfer it over, and good luck. All
right, welcome back for part 2. So here we have more 2-dimensional motion problems. So we've talked about things traveling in 2D, like an X and a Y. all right, and it travels up and it goes around, or it might make this arc shape. But there are other ways of saying two-dimensional motion. One of them is circular motion. Anything that completes circles, right, in a path, that's traveling in 2 dimensions, but it's doing it in a very specific way. Okay, it has to be a nice uniform circle that it's traveling around, and it usually travels with a constant speed as it travels around that circle. So here's some examples. Your book calls it a stone. You tie a rock or a stone or a model airplane or something like that. You tie it to a string. The string has a specific length, and you twirl that around, and it looks like something that is being swung in a circle, a circular path. That's circular motion. Okay. Another example here is the moon. The moon travels around a planet in a perfect circular orbit. Okay, so it just moves around. Now, it usually doesn't quite happen. There's other things that factor in, but it's a good example that you can think about. Another example is you're in a car and you get stuck in a roundabout, right? You just travel round and round and round that roundabout, usually at a constant speed. Okay, so these don't have to be at constant speeds, but that's usually how we're going to get away with the problem, is using a constant speed. When there's a constant speed, that's what we call uniform circular motion. Is a constant speed changes it to the word uniform circular motion. So speaking of the car in the roundabout, that's the one we have here for our example. It's a top view of a car going around and around in a circle at a constant v. If you were to track this car as it went around, you will see a couple of things. You see that one, the radius remains the same. Okay, the radius initial and the radius final are both the same because the circle is a uniform circle. You'll also see that the speed never changes. Your initial velocities, your final velocities are always the same. They're at different angles here than your position. They travel up here like this. But they're equal in magnitude, just different in direction. Okay? If we compare these two vectors over their scalars, okay, so this is just some math that we do in the book, but you'll have a change in v because vi and vf are the same, but you will end up with a change in v based on that velocity. Okay, higher velocity, higher change in v. You'll also end up with this radius, right? So you'll have a change in r dependent on the radius r. Bigger the r, bigger the change in r. Okay, so you'll have these two equalities that kind of come out of this. And again, more in your book goes more in depth on this. But if we take this newfound information that we have these two equalities that match each other, if we plug this into our equation for an average velocity, which would be the change in v over the change in t, okay, we end up solving out for the change in v, which means I'm going to have to multiply the scalar v to the other side, the velocity, and we'll end up with this equation, which is velocity times the change in r over our scalar product r times the change in t. Again, this is just a mathematical exercise. You're going to be given a lot of where this is going is that it gives us a new acceleration. Not like our old one. It gives us a new acceleration. And we call that the centripetal acceleration, which I discuss more in the next slide. But that's why we give it a little bit of a c here. How did I get a v squared here? Okay, well, our velocity is here with our lowercase v, and then the change in r, that's a change in position. That's a change in position. So that's actually a displacement. Displacement over time, change in position over change in time, this is our original velocity equation, change in position over change in time. So it's just adding another v. So we have a v times a v, so that's how we get a v squared, and this all goes over the radius. So this is a different acceleration, okay? And you can only use that acceleration in uniform circular motion. So we call that specifically the centripetal acceleration. It's a lowercase c on the front there. It's just to remind us that you can only use this for circular motion. There's a couple of other terms that come out of circular motion. One of them is known as the period. Okay, we denote that with a capital T. That's why we've been using lowercase t for time, because an uppercase t is devoted for period, a specific time. This time is the amount of time that is required for an object to travel a distance of one full revolution. Okay, so you got things moving into circles. It's the time it takes to go from any starting point all the way around the circle back to that starting point. That's known as a period. You know periods. The period of the Earth right now going around the sun would be about 365 days. Okay, so that's the period of a year. 1 year's travel is one rotation around the sun. Okay, so that's an example of a period. Period is a unit of time. Using what we know for period, we can make an equation for it, right? We know that the velocity is equal to a distance, or speed, I should say. The speed is equal to a distance over the change in time. So back in chapter 2 when we talked about speed. Okay, notice we don't have any vector components here, so everything is non-vectored, which means it's a speed. So the speed is a distance over time. Well, what's the distance that we travel in one period? Well, that would be one full revolution around the circle, which would be the same as the circumference of the circle. Okay, so the circumference of a circle is 2 pi r. So for the distance traveled, I'm going to plug in 2 pi r. The time it takes to do a distance of 2 pi r, this is the period t. Now if you rearrange that equation, you'll end up with this over here. You end up with a period t is equal to the total distance, 2 pi r, of one revolution divided by the velocity at which that revolution is occurring. Okay, so that's one way of finding periods. We'll have a couple of practice problems on that as well. There is a couple of others. Before we dive into practices, let's do a couple of others here. Another variable used for circular motion is the angular speed. Okay, so remember v is our straight line speed, our linear speed. Angular speed is just slightly different. Okay, if we look at the comparison between these two, when something is moving in a circle, right, it'll travel some distance, and in here they call them arc lengths when we do it in circles, but it's just a length. It's a distance traveled nonetheless. Linear speed would be denoted with v for velocity or speed. S would be the distance that it traveled. So in here we're calling it an arc length, or it's just the distance traveled s. And we divide by t, the time it takes to go from one point to the other point. An angular speed we give a different value to, and we call that one w, or omega. It's a Greek term. It relies on not the distance, but the angle at which it has rotated through. So instead of s, angular speed looks at the angle that it travels through, theta. So this would be a theta divided by t. How many radians or degrees did it travel in a specific amount of time? It's angular. So if we take this and we run up here, and we compare it to our period, okay, that means the t on the bottom will get replaced by a capital T for period. The angle that it transverses in one period, okay, would be one full rotation. Okay, so period here on the bottom, one full rotation again on the top. One full rotation when we're using radians is 2 pi. 2 pi radians is one full rotation. Now, traditionally, we use radians for these angles so that we can get that factor of pi in there. We don't deal with degrees nearly as much. Not that it would be wrong to say 360 degrees up here, but degrees is not the SI unit that we are looking for. It is radians that we are looking for. So if you are confused about that, check it out, send me an email. But 2 pi radians is the same as 360 degrees. It's one full rotation. And this will give us then the angular speed, being that it is a angle over a time. Okay, hopefully we see the difference. This I can convert. I can do a little bit more on it. If I want to see what omega is in terms of, say, a radius or regular velocity, I have the term for period on the previous slide. Period was being 2 pi r over v. If I take it and I plug it in, b and t is in the denominator, the equation flips, I end up with here. I end up with omega, the angular speed, is equal to 2 pi times velocity over 2 pi r. 2 pi's go ahead and cancel. That's why we use radians, is for this nice cancellations to occur. And we end up with v over r. Okay, v being the linear speed, r being the radius of the circle, w being the angular speed. And if we rewrite that, we can see the relation between the two. You have linear speed, v, is equal to its angular speed, w, multiplied by the radius. So the bigger the radius, the bigger the linear speed it would be to do this. And you can kind of see that as well. So let's assume that you're holding hands with a bunch of your friends. You're all in a big line, and you're going to swing around in a circle. So the person that's in the center of the circle stays still. Okay, they stay still, but they just rotate. Right? Well, the person that's holding their hand, okay, the next person holding their hand over, if this person rotates, the other person has to rotate as well, but they're not the pivot point. They have a radius, right? So they have to move a little bit to get out there. And you can kind of see as you go farther away, all these people are holding hands, that the outer person has to move a whole lot faster than the middle person because the radius is bigger. We are going to discuss this in much more detail later in the class as well. This is your first introduction to it. But know that the angular speed, the differences between the angular speed and the linear speed is a great starting point to come into this. Okay, so how does this work here? We have our angular acceleration equation, which is just v squared over r. But let's say I don't know what the linear speed is. I only know what the angular speed is. Maybe that's what's given in the problem. How do I convert that? How do I get things to go around? Well, we have the equation now for velocity that puts it in terms of angular, right? So if this is v squared, if this is linear squared, I can replace it with rw, and this would then make it angular. So rw squared over r is going to mean that our centripetal acceleration is equal to a radius times our angular speed squared. So for instance, if you have a question that only gives you those variables, you can still solve for these things. So it's all about knowing what we're talking about, how they're related, and getting everything to work together. So I do understand that's a lot of equations to cover in a chapter. Lots of examples are needed. So we'll go ahead, we'll do some more, and we'll get you a better understanding of it. And then your homeworks as well also have lots of equations, lots of questions, to put you through some practice to get used to these things before we move forward.
Okay, on to some centripetal motion problems. Different little bit of a different two-dimensional motion. So we've got some new equations I got written up here that we went over in lecture that we'll be using in these problems here, these examples. So the first one we have example for, it's a disc thrower. I guess you see these sometimes at Olympic sports. You can rotate around, throw a disc a very long distance. Anyway, a disc thrower takes a disc in their hand that weighs 1 kilogram and then rotates it into a circle. So they rotate into a circular path with a radius of 1.06 meters. While they're twirling around, that disc can reach a speed of 20 meters per second. The question here is, what is the radial acceleration of the disc? So there's a lot of different vocab and terms that different books in different places are going to present with you. Radial, of course, you have radiuses when you have circles, so you can think of it as circular acceleration, centripetal acceleration, all those things take place like that. Okay, so we have a radial acceleration of the disc. So this is what it's referring to anyways, that we do have something spinning in a circle. It is asking for a radial acceleration or a circular acceleration. So I've drawn a little pictorial over on the side there. We have 1.06 meters for the radius. It is traveling in a circle. In this case, it doesn't matter if it's clockwise or counterclockwise, but it is traveling with a velocity of 20 meters per second. Now, I know that it is velocity and not angular velocity or angular speed because the units meters per second is where it's traveling. Meters per second, of course, would be the velocity normal linear speed that we're used to seeing. So I can denote it as a v. For this example, it's pretty straightforward. It's not too bad, quick and easy anyway. But we need an equation. We're looking for AC. A centripetal acceleration is what we're looking for. And we have an equation that has AC in it up top. It's v squared over r. So the v that we're using, it's already in regular terms of velocity. So we would have 20 squared over the radius. And the radius is given to us very plain as 1.06 meters. So when we go ahead and we just do that calculation out, what you'll get here is 20 squared being 400 divided by the 1.06. And you'll get an acceleration, a large acceleration of around 377 meters per second squared. All right, 377 meters per second squared would be our radial acceleration that it's trying to get out of there, centripetal acceleration. Okay, another example we can look at here would be something like the Earth and the Sun. So this is, I guess, example 5. Get that changed. Example 5 here. What would be the centripetal acceleration of the Earth as it orbits the Sun? It does give us one bit of info. It says the distance between the Earth and the Sun is 1.5 times 10 to the 11th meters. Nothing else to go on this one. All right. So, well, here we have the Sun. Here we have the Earth. It travels around, and here we have our radius of the Earth Sun system. We need to find centripetal acceleration, so I guess I'm going to start with that equation, which of course is one of them that we have here. The centripetal acceleration is v squared over r. We have a couple of different ways of getting there, depending on how we do this out. I do know the radius given in the problem, 1.5. So all I need to do is find v. Now, v is given in a couple of different terms. The velocity, we have it as r times the angular velocity, but that isn't given either. Otherwise, we do have it as period is equal to 2 pi r over v. There's a v in that. And let's see, that incorporates r again. I know what r is. I know the radius. And it involves a period. And I can solve for the period because I know how long it takes for the Earth to travel around the Sun, 365 days. So I can do that. So that seems like a good path, right? Sometimes think this out, figure your path, and get there. So let's go with that. Let's take the equation here for period. And we'll multiply both sides by v and then divide by t. So we'll have v is equal to 2 pi r over t. All right, so I'm just swapping these around, multiplying by v and then dividing by t. Just rewriting the equation so that I can take that and plug it into our equation over here. So now v squared is going to become 2 pi r over t squared over r. Okay, hopefully that makes okay sense. Okay, so now what do I have going on in there? Well, let me do some cancellations. Let me knock some things. Out of here. So if I distribute out that square, right, I would have 2 being squared. That would give me 4. I'd have the pi being squared. That just gives me a pi squared. I have the r being squared, so I'm going to end up with an r up top. The t will get squared in the denominator, and it'll get pushed into the lower denominator here. And then I'm, of course, still left with this r down here. Okay, so I've just distributed the squares, and I've cleaned it up a little bit. Now r divided by r, that's going to cancel out. So one of these r's cancels with one of these r's, and I'll be left with that. And what does that leave me? 4 is just a number. Pi is just a number. R is going to be in meters. But T, the period of the Earth, is in 365 days. Now, that's not quite the correct SI unit, is it? So we would have to do a little calculation on that. So I would have 4 pi squared. R is 1.5 times 10 to the 11th meters. Now T squared, if this is in meters, T, time, needs to be in seconds, so I can square it and get an acceleration of meters per second squared. So I need to figure out what 365 days is in seconds. So how do I do that? Well, that takes us all the way back to chapter 1, and we need to do a unit conversion. 365 days, and I need to multiply this out, right? I want to get rid of days, so I'm going to put day on the bottom. 1 day consists of 24 hours. Get rid of days. Okay. And now I need hours to get out of there, so I'm going to put hours down below. How many seconds are in 1 hour? If you remember, it's 60 times 60, so it's 3,600 seconds are in an hour. Okay, so it'll kill off hours. Sorry if that's getting a little bunched up there. 3,600 seconds. Okay, so now all that's left is seconds. We have converted that into seconds. So now we just do the math. 365 times 24 times 3,600, and that all gets divided by 1. And that will give us the amount of time in seconds that it would take. So this comes to 3,153,6,000. So there's a 31,536,000 seconds are in a year. Okay. We need to take that number and we need to square it. This definitely isn't something that's happening in your head. You want to go ahead, plug this into a calculator, and get an answer. And I'm going to punch it into mine. See what I get for the numerator. I'm getting 5.9 times 10 to the 12th. And we're going to take that and divide it by 31,536,000 squared. All right, and we get a number here that is quite small. 0.006 meters per second squared. Very small. Okay. So that's quite an interesting problem. The Earth does have a very small centripetal acceleration, partly because that radius is so large that the Earth doesn't need to move very quickly with an acceleration compared to our discus thrower from the previous problem. Okay, we'll box the answer, and that one's good to go. Just out of curiosity, if we were wondering what the angular speed of the Earth was, we can do that out. Let me get rid of my side work here. If we were looking for angular speed, what is the angular speed? Angular is special. It means that we need to be talking about angles and not linear. So what is the angular speed of the Earth? Okay. So in this one, it's looking for what is W, because it has angular in front of it. It's looking for W, the omega. What is the angular speed of the Earth? Okay. Well, now that we have some numbers to go off of, we look up and we look for an equation that has our omega in it, right? Our omega ends up being here, tied in with V. Okay, so what's the best route to go with this one? Well, we have a couple of options. We already know the acceleration, the centripetal acceleration. So I wonder if we took the centripetal acceleration, and if this is v and this is v squared, if we plug that in, we would get an r squared omega squared over r. Right? Okay. So then one of the r's here cancels with one of the r's there. So we would have a centripetal acceleration of r times omega squared. Okay. Might be able to make that work because we already have AC. We already have the centripetal acceleration. All this would then be is omega squared, which is what we're looking for, times r, which we already have. That's given in the problem. Okay, so this would mean that our centripetal acceleration, 0.006, is equal to our omega squared times this very large radius. Okay, the 1.5 times 10 to the 11th. All right, so how do we solve that? Well, we need to divide over, and we need to take a square root. So let's go 0.006 and divide by 1.5 times 10 to the 11th power. If you are using a calculator to do these, parentheses are your friend. Once you're all done with that, you should get around a 4 to the negative 14th, and then take a square root of that, and you should get an answer for W of about 2 times 10 to the negative 7. Okay. Oh, let's see, my camera's just a little bit off. 2 times 10 to the negative 7 would be the angular speed. Now, what is the angular speed? Some people would call that radians per second. Your book actually just refers to it as inverse seconds because they don't classify radians to be a traditional unit. So you might see that a couple of places. 2 times 10 to the negative 7 radians per second, or 2 times 10 to the negative 7 inverse seconds, or just seconds to the negative first power.